So, am I audible? So, myself, Arvind Pandit. I have just graduated from IIT Dharwad, and now I'm working as a full-time as an R&D engineer at Indrones Solutions. So, the topic for today's presentation is ROS-based multi-agent system simulation control testbed, which we call as mascot. Okay. So, coming to an overview of the presentation. So, we'll start with an introduction, followed by the preliminaries, where in preliminaries we will talk about how our the solution which we are giving, so how mathematically it is modeled and all. Then we'll come to the mascot structure and features. Then the example what we have already implemented, and followed by the conclusion and future works. So talking about the multi-agent systems. So what is multi-agent system? So multi-agent system is just a fancy word for, swarm is a fancy word for multi-agent system. So in multi-agent system, the main thing is different agents. Now those agents can be either drones or ground robots or any system which cooperate with each other and performs any task. And on multi-agent system, we have a distributed control where the control is distributed among each of the agent, like divided among each of the agent to achieve any goal. So each agent will be having its own local control algorithms, and which will be communicating with each other over a communication channel. In our case, it is on a ROS. So what are the advantages? So we can achieve complex objectives, faster exploration, etc. using the multi-agent systems. And also the main use case are towards the robotics, space exploration missions and surveillance. So let's talk about the simulation platform. So I guess everyone is aware about ROS and simulation, so I don't need to give much about why we need simulation. So just a brief. So we need to test the performance of a robot, how it works well before deploying it in the hardware. So we can evaluate the different control laws which we have developed for our system. And if there is a training purpose, so as AI-based systems are getting too rich, so we have to perform some kind of training. So simulation environment is a very best platform to train in a safe and hazardous-free environment. And also study the behavior, how our model works. So there are many existing simulators. So when I talk about multi-agent system, so I mostly refer towards the number of drones. So there are many simulators, MATLAB-based simulator as well as others, which provide this facility to control, to check the control algorithms. But those are either limited by number of agents or those are not directly deployable to the hardware or in the real life. So then we came to mascot, which we have developed. So when I was working when I was a student at IIT Dharwad, so there was a small gap between the theoretical research where people were developing different algorithms, distributed control algorithms such as consensus, time-based consensus, etc. But they were just testing in MATLAB and publishing the paper. The thing was, those things were not seen in the real world. So that gap which I have observed, and on that we all worked on, and we tried to develop this platform using ROS. So it supports a low-level driver, as well as we have provided a very simple user interface for the researchers, so they don't have to take care about the spawning the robot in a gazebo environment, etc. They will just have a configuration file which they have to set up, and then things will work. And also we have provided a Docker support for it. So you can see just a figure of it. I don't have any video for now. So as you can see, at the initial time is equal to 0 second, all the agents were at some random places, and then consensus algorithm was initiated, and everyone gets aligned to the 1. So let's talk about the preliminaries. So this is a basic model of a drone. So dynamics model. So as everyone might be aware, so there will be 4 propellers, so specific towards the quadcopter. So 4 propellers, so there will be 4 thrust, T1, T2, T3, and the summation of each will give you the total thrust. And this is, there are 2 frame of reference, earth frame and base frame, where base frame is the frame of a drone. So the total upward thrust in z-axis will be given by the summation of each individual thrust, which is dependent on the angular speed of a propeller. And so the translation dynamics of the quadcopter in earth frame will be given by this equation, where as you can see there is an mg term which is gravitational pull, and you have to rotate the thrust from the base frame to the earth frame, and also there is a velocity. So these are the translation dynamics. Similarly for the rotational dynamics, so torque along the x-axis and y-axis will be given by this equation, and the torque along the z-axis means yaw moment will be from this. So the overall quadcopter motion equation will look something like this. So now coming to the main contribution of Earth. So in normal drones are not modeled as a double integrator system, but the thing is double integrator system makes it very easy. This approximation makes it very easy for to allow different control laws to be tested. So we have modeled it with an assumption. So from after the equation you can see that can be modified to get this matrix, and with a very small assumption that the roll and pitch angle will be very small, we can approximate that equation by the following one. And using Newton's second law of motion, we can get the roll and pitch angle directly from the acceleration in x and y axis. So this was the idea. So we have developed a gazebo plugin which replicates this model of a drone. So for the development of mascot, the tools which were used, I don't need to introduce these things. So ROS, which is a distributed architecture. So we have used ROS for our main intercommunication. Our simulation was obviously on gazebo, and the plugin which was developed with the help of simulator, term simulator, which is an package for an AR drone. Everyone might be aware about the AR parrot drone, right? So same drone is used in our system, and this is the main control block diagram. So as you can see, there are position control loop. The basic control loops are altitude control and heading control, and there is an attitude control. Overall, there is a position control loop. So this is a basic architecture of ROS. So where all the control firmware is handled by ROS, and our simulation and system plugins are in the gazebo, and both are communicating over the network. So talking about the features. So as I told you, we have tried to make it very simple for the researchers to deploy their algorithm. So they can directly set these configurations, like what all robots they want to deploy, how many of the agents they want to get into simulations, what will be its position, and what are the examples. We have also provided few example control laws, which are waypoint navigation, consensus, and min-max consensus. So talking about few examples. So the first is waypoint navigation is a very simple position controller, PD, and you can see the plots output which we have got for our system. Second was the consensus algorithm, where we have tried both leader follower as well as leaderless consensus. So this is given by this following equation, where the first equation is for the followers, and if the agent belongs to a leader group, it will be controlled externally. Our control algorithm won't be controlling it. So these are few plots of you can see there were 4 agents, and the circle shows the starting position of those agents, and after the control algorithm start, they all get aligned to a single position. Similarly, there was a leader follower which was following the one robot which is in orbit. So similarly, those were the linear control laws, and we have also tried some non-linear control laws, which is min-max time consensus. So these are the result graphs for the same. Now, coming towards the conclusion and future works. So to conclude, simulation platform was developed mainly for the researchers so that they can easily deploy their distributed control algorithms on a more realistic world. Then the main part, the quadcopter, was approximated as a double integrator system. Then various linear and non-linear control laws were tested and examples were given. And this was the integrity of our developed testbed. Now, our future work, obviously this is an open source work, so everyone is invited to contribute and expand it. We are also working towards it, and now the plan is to get an hybrid model where few agents can be in the simulation and few agents can be in the real hardware. Like if you have a Crazy Fly or any hardware drones, so, and few of the agents can inside be gazebo, and they all will be communicating with each other. And also we are planning to have an UGV UAV setup, like one agent can be an UGV ground vehicle and the other drones. So this kind of setup is very useful for the rescue and surveillance operations. And very important upgradation to ROS. So this package was built last year, which is still in ROS 1, and we are working towards the upgrading it to the ROS 2. So thank you for the listening, and this is the thing which you can check. Before ending, I want to share something about my recently joined company, which is Indrones. So we are Indrones Solution. We are working towards the surveillance and mapping of an environment. So we mostly have projects in which we do kind of mapping of railway, oil, gas line, pipes, etc. So our main research domain is towards the development of hardware of the drones, computer vision, mainly towards the 3D reconstruction and AI ML based object tracking detection. And we have a few software platforms where we where for the live demonstration as well as data monitoring. So if anyone interested in the drone area and computer vision, please check out the link. Okay, that's all from my side. Thank you.
Sure. Thank you so much, Arvind, for the talk. Thank you.